Jai Hind everyone. I Neeraj Sharma, Assistant Professor EC Department at AKGEC Ghaziabad. I am before you to present the video lecture for the complex topics for the subject antenna and wave propagation. As per the AKT scheme, its code is KEC 603. So this is my third lecture for this subject. Here for this subject, initially I have recorded although the two videos, which one is related to the subject antenna wave propagation from unit 1 and 2, and they are basically or mainly focus onto the electromagnetic field part, basics of electromagnetic field part, and their applications I have able to explain in that lectures. So now, as per the name suggests for the subject antenna and wave propagation. So specifically to this subject for today's my lecture will devoted or concentrated on the topic antenna. Okay, so for this term antenna. So basically the antenna simply a very easily device that is available with us at 24 hours in the present scenario. Either we are at home or outside the home. Because the mobile phone we are carrying with us at 24, although almost time, and also when we are coming at home, if we are using our TV setup, television, that is also using the running with the help of only this term antenna device. And also when we are moving out of the house, where we have not the television, but itself we have although we have the mobile phone with us, but the towers that we are situated around our houses, that is also for the communication of this mobile technology, that is also using the main component, that is the antenna. So for this term antenna, this is a device that is available, and all the things what is going on with this that is invisible, that we can experience the functioning of this device with the help of the other devices like mobile phone or something else if we are using, that are totally concentrated or connected with this antenna. Then we are able to say that this antenna is working. Otherwise we are not able to visualize, only just we are considering that it is working. So here as per the importance of this subject, if I will say, so because of we are mainly here studying with the subject regarding the for the invisible things that we cannot see, for that we want to going to study. So as per BTech third year BTech student or electronics engineering student, that is our responsibility to understand the main basics of antenna. So if we are going to and somewhere someone will ask with us to what is this antenna, because you are from the electronics engineering domain. Okay, so in that point of view, how we will define? So for that point of view, we have to the basic information of this antenna. It is a device that simply looking in a structure, conductor based structure, that we are metallic conductor structure, that is we are basically looking it. But as per the functioning, how it will work, so we can understood. So for that point of view, as per our syllabus also, which has been designed from our university. So for that point of view, we will see. So the third one unit for this subject is basically mainly focusing on to the basics of this antenna. What are the basics that we have to study to understand the working or the functionality of any antenna structure? Either it is a tower we are using, or we are using in mobile phones, or we are using for the television also. Okay, so for that point of view, I am here considering the main two terms, gain and the directivity. I have considered here for this video. So here I will discuss mainly onto these two topics. What are these device these parameters, directivity and gain, and how it relate, and how it will able to explain the functioning of any antenna structure. And also I will try to relate these parameter with the other parameters of antenna, that is also useful for antenna designing or the study as per as the practical point of view also. Okay, so here number of terms will be here like radiation pattern, beam width, HPBW, directivity, gain, effective aperture, effective height. Okay, so all are the parameter, beam area, like main lobe, side lobe. These are the basic content, basic parameters for any antenna study of any antenna structure. So in these all, I am focusing on these two, gain and directivity. So first one, that is the directivity, then I am going to explain here. Just simply if I am considering the case of any street light, let's say any street light is situated somewhere or mounted as on the streets, and it will giving some light to the in the night, so we can visualize and move forward onto the roads. But they have a limitation. They can able to only the same intensity what they are getting, and they are able to visualize only the some near about area which is limited to the distance. But if the same thing, same power, if I want to use to move it for a long distance in spite of the limited distance, then what we are using, the same concept we have to discover, that is the another this will light system we are using applied onto the torch. Okay, so in this torch, that what we are doing, that is aligned this all power which is spreading around all the area, that will suppressing this power and pointed out to the in a specific direction. That means when we are concentrated this power into some specific direction and reducing this its area and increasing the distance. So that's why what will happen, we are able to look forward for any extent distance in spite of the limited distance. So that means what we have done there, that we have a study in our natural or our daily examples, we can see this. So for that, what we are just now giving the direction to the and focusing all the light to the specific direction. So this concept of concentrating the power in a specific direction simply named as a directivity of any antenna. So this directivity term that has been introduced, and also it is related with the gain, that I will further explain in the next slide. So directivity, first we are defining, I am defining here, that means we are given the direction. Okay, so directivity here it is defined as the directivity of antenna is defined as the ratio of radiation intensity in a given direction from the antenna to the radiation intensity averaged overall direction. That means what? That example of street light that I have given, that also just means we are just considering an antenna and we are considering the isotropic, just its behavior, that if we are not doing any modification in that, and it will spreading the power, means it is radiating in the all directions, average power. But when we are compressed this and moving this power to a specific direction, then it will termed as the directivity. Okay, so here this is the ratio of the what we are power, maximum power that we are transmitting in a specific direction, and what that antenna is able to describe, able to radiate in all over in the overall direction. So the ratio of these two parameters simply named as the directivity. Okay, so the average radiation intensity for the any antenna, that is equal to the total power radiated by the antenna divided by 4 pi. That means P radiated over 4 pi. This is the average power formula for the direct average power. Now we are defining the power in the terms of radiation, and we are defining the directivity in terms of the radiation intensity. That is D is equals to U over U naught. This is the radiated power intensity in a specific direction. This will be the average. So we will put this average value onto this one. So this D will become U 4 pi into U by P radiated. So this is the one of the definition for the directivity. Another, the directivity of antenna is the also what it can be average power in terms of power. If we will say our definition, this definition is based on to the radiation intensity. If I will consider it into the power density in the form of power density, so that will be the ratio of the maximum power density to the average value of over a sphere as observed in the far field of an antenna. So this is the another definition for the directivity in terms of the power density. So this value is now given by directivity, which is also assigned by or symbolized by this parameter d. So this d is equals to, if in terms of power density, that is P of theta comma phi max to the P of theta comma phi average. So this one is the now another definition. I usually for the antenna practical designing, this value of d is always we will keep greater than or equal to the 1. So now if this will be the simply the definition of this directivity. Now one another important parameter that will be regarding this antenna with reference to this directivity, that is the beam area. That means which power that is specified in a specific direction, which will having also the beam its area. So that's why the specific area where the power it can be, it will radiate. So this will be the beam area. So now I am here, I will try to relate this beam area with this directivity. That is also an important derivation from the examination point of view, also as far as the relation with this directivity and beam area, how they are mutually related to each other. Okay, so for this point of view, as per this formula that is written here, P theta comma phi max over P theta comma phi P average value. So for now the P average value, if I will calculate, so the average power density, that is given by the formula P of theta comma phi average. This will equal to 1 upon 4 pi, phi is equals to 0 to 2 pi and theta will be 0 to pi. P of theta comma phi sin theta d theta d phi. So this will be the value of this average power, and also we can write this one, this formula, this one as the 1 by 4 pi, and this limit when we will solve the this for theta and phi, it will comes equal to the 4 pi, and this will P of theta comma phi d ohm. We can also write it like this, where this d ohm is equals to the sin theta d theta d phi, and it is in the steradian. That will be the d ohm, that is the beam solid angle for this any beam. Now after that we will put this value into this directivity form. D is equals to that we have already defined in terms of power density. So for that, when we are doing this one, so what will happen now, then D is equals to formula, that is P of theta comma phi max to the P of theta comma phi average, and put this average value, this one or this one, to the this equation. Then what will happen when I will write it here? So P of theta comma phi max, that is 1 by 4 pi. Its value I am now putting here, 4 pi P of theta comma phi. Okay, then also what we can write it here, dO, and dOm is equals to sin theta d theta d phi. So after we are making some arrangements here, so divide 1 by 4 pi, we can also write it like this, P of theta comma phi divided by P of theta comma phi max. Okay, and this one dO. We can also write it like this. Okay, so here you can see this term P theta comma phi divided by P theta comma phi max, it will be the also the form of normalized power. This relation we treated as a normalized power. That means we are normalizing this power. That means whatever the value of any parameter, when we will divide that value with its maximum value, the resultant what we will get, it will named as a normalized term. So P theta comma phi divided by P theta comma phi max, this will equal to the P of n theta comma phi. Okay, so this will be the normalized power. This will be the normalized power. So this will d is equals to 4 pi over, we can also write it like this, 4 pi Pn theta comma phi dO. Now the above relation will now reduces to the this in this form, and also when we will relate this term only, this will equal to the ohm A, that is the beam area of any antenna. So we will ohm A is equals to in double integral of 4 pi means around sphere Pn theta comma phi d ohm. So this relation will becomes d is equals to directivity will become d is equals to 4 pi upon ohm A. This equation will give the relation between the directivity relation between directivity and beam area. So this is one another important relation between the directivity and the beam area. And also if we want in the next we will see this. So this one beam area, and for isotropic antenna directivity is always will become 1, and for the short electric dipole its value will be 1.5. For some important terms in this, for isotropic antenna its value will be 1, and also for any dipole, this d is value will be 1.5 or 1.76 dB. This is another important conclusion when we will for practically when after designing and the calculation of this directivity, we can also find out the value by using these formulas. We can calculate the value of the directivity, and for short dipole, that is the short wave or half wave dipole, that is the 1.5 or 1.6 dB. Basically mainly this term will ask also into the many competitive examination. So for that point of view you can recall or remind it or use it for the examination preparation. Okay. So, and also for the interview point of view, there's sometimes in the practical for the designing in interviews from the subject antenna, these questions may ask. Next one, that is the gain, another form. This is simply gain, that we will know that the ratio of output to the input, that will be the gain. Means what actually we are in power we have, that we are already transferring in spite of the what we are getting and how much it will transferring. So, for that point of view we are using. So, the gain and directivity are also the same thing, but when we are antenna, just simply if I will say directivity that we have defined in particular direction, that will also into the gain term will also define into the onto the basis of this direction. But main change, how much in the direction where it is transmitting, but how much, what is the efficiency of this antenna is able to transmit that or radiate that power. When we are considering in particular direction with the efficiency of that power, then that term directivity will become the gain of this antenna. Okay. Means just we are considering is the physical efficiency of this, how much actually it will, if I am giving 100% power. So, in terms of how much it is now transmitting, when we are multiplying it with the direction, then it will become the gain of the antenna. So, G will also related here, gain will given by assigned with this parameter G, and G is equals to eta into D. That is one another important relation between the directivity and the gain. G is gain, D is directivity, and eta will be the efficiency of that antenna, for which we are defining this term gain. So, the gain of an antenna is defined as the ratio of the intensity in a given direction to the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotropically. So, some another definitions here, the gain of antenna, simply another terms of defining for this gain that I have explaining here. So, that is the gain of antenna without involving the antenna efficiency is defined as the ratio of maximum radiation intensity in a given direction to the maximum radiation intensity from a reference antenna produced the same direction with same power. That means for we are just defining onto the comparison, and the same power we are giving for to the reference antenna as well as the what we are the antenna which we are using. Similarly, to the extent to which a practical antenna concentrate its radiated energy in a given direction in comparison to the reference antenna, that what we have defined in the above point 2, then this gain will become the directive gain. Also another thing, so the directive gain is defined as the ratio of the intensity in a given direction at a given direction at a given distance to the radiation intensity that would be radiated at the same distance by the isotropic antenna radiating the same total power. So, the power gain is also another form that is defined as the ratio of the radiation intensity in that direction to the average total input power. So, in terms of power, we are named it as an power gain. This is also the form of gain, and it is given by gain is equals to 4 pi into radiation intensity divided by total input power. So, these are some another different form. One another, that is the relative gain. When we are considering this power gain with some reference antenna reference direction, so that gain will become reference gain, relative gain. So, this relative gain, which is defined as the ratio of the power gain in a given direction to the power gain of a reference antenna in reference direction. So, the power input must be the same for the both antenna. Okay, means we cannot change the power. That means for reference we are giving some, let us say, power P1, and for the designing antenna we are giving P2. It is not possible. If for the comparison point of view, again we have to calculate the same power we have to give in for the both. So, this is the relation for this G. Another, the ratio of the gain to the directivity is the antenna efficiency factor that I have already here discussed. When we are directivity, when multiplying with this term efficiency, then it will become gain of antenna. One another form of gain can be measured by comparing the maximum power density of the antenna under test with a reference antenna, that is also known as a gain, and for the short dipole. So, this is another form of gain that we are relating here. In the same way, We can also define this directivity. We have related this with the beam area. We have I have related this with the beam area, this term directivity, but beam area having the beam and it will have some half power points there, means half power point in the theta plane as well as in the in the phi plane. So, in this configuration, when we are using this gain, these two in terms of as a beam area, with that we have already defined that beam area relation between this half power angle, that is the beam area ohm is equals to theta hp into phi hp. So, we can put this formula into d is equals to 4 pi over ohm a, and when we will solve that value, then the directivity will given by 4,12523 degree divided by theta hp into phi hp. So, this is the relation between the half power beam width, half power points with the directivity. So, here theta hp, that is the half power HPW in one principal plane, and phi hp HPBW in another principal plane. That means we are giving what we are saying in a half power points in theta plane and half power points in the phi plane. So, this will one another the important relation between this directivity. Next one, that is the effective antenna aperture. So, what will happen if antenna aperture simply we know that the area, but what will happen, let us say if any antenna that we are looking or that is situated around roofs or somewhere, that we are saying it has some specific area, we will treat that it's an aperture. Okay, antenna aperture. That, but it is what? That is the physical aperture that we are able to, we are looking at. But when it is we are receiving, considering an antenna with a receiving mode. Okay, when we are considering it in a receiving mode, then what will happen? The power, let's say, coming from any direction, and antenna, let's say, put here, we have now placed here, then power is coming and striking onto this aperture. But what will happen? Around the side walls of this aperture that we are looking, here the field value will be 0, means it is not receiving any power, but along this besides all these corners, the area which is specifically receiving the some power. As you can see in this picture, this will a horn antenna that we are considering here, and these side walls, let's say we have the field value will be 0 here, it is not receiving, but other than is area where this antenna structure or aperture will receiving the power or transmitting the power. So, this part which is effectively participating, that means we are considering the structure with some conditions, not with its realized or its actual position, but with some specific condition when we are considering, then it will become the antenna effective aperture. That means the part where the antenna is area from where the antenna is receiving the power or transmitting the power in spite of the complete aperture. So, this will simply known as the effective aperture of antenna. One is the physical aperture that we are looking here, which is denoted by this term AP, that is the physical aperture, and one another that is the AE, this will the effective aperture. So, for that point of view, as you can see this, because we want to make the relation with this effective aperture to the, if I will say to the directivity. So, that let me see. So, this will be the effective aperture that you are looking here, and the power that is now incidenting, and this power will be, let us say, P is equals to given by E square by Z, AP is equals to S into AP. After that, now what will happen? So, when we are comparison first, that will another important term that is introduced here, that means two terms that we have considered here, AE and AP, physical aperture and effective aperture. The ratio of effective apertures to the physical aperture, that will defined as the aperture efficiency, this one. So, consider an antenna, now an antenna with an effective aperture AE which radiates all of its power in a canonical pattern of beam area ohm A. Let's say this one transmitting this power from this antenna, it is transmitting and this will be the ohm A, that is the effective part where which is able to radiate into the specific direction from this effective aperture area. So, assuming a uniform field EA over the aperture, the power radiated is given by this term, P is equals to EA square by Z naught into AE. Then assuming a uniform field ER in the far field at a distance R, the power radiated will be given by this term, P is equals to ER square by Z naught into R square ohm A. This will be having the relation with the distance, as well as we are considering these two terms, distance as well as the beam contribution. Okay, so we are comparing. So we are also using another relation in this here, ER is equals to EA into AE by R lambda, that is also defined, and we will put this value into this equation, and after simplifying we have to compare these two equations, and after comparison we will get the relation that the lambda square is equals to AE into ohm A, and D is equals to directivity, that we know that 4 pi over ohm A, and put this value ohm A here. So 4 pi upon ohm A value will be lambda square over AE. So D will become, directivity will become 4 pi into AE by lambda square. So this is another relation that you can see here, D is equals to 4 pi into AE by lambda square. This is the relation between the directivity and the effective aperture. So here I am, this will be the relation. So I am able to explain this or demonstrate the relations of this directivity with beam area and the effective aperture, and these are also useful for the antenna study. So thank you and Jai Hind, and this is the reference book that I am using here, that is the for the book that we are considering here, the JD Cross for principle of antenna. Thank you.